Hey everyone, and welcome back. Today, we're going to crack open a classic coding challenge. It's all about finding that common ground, quite literally, right at the start of a bunch of words.
All right, so let's just jump right in. Forget about code for a minute. Seriously, just look at this and ask yourself a simple question. What's the longest start these words all share?
Okay, so take these three words for example. Flower, flow, and flight. Now, I bet your brain just, poof, spotted the answer almost instantly, right? But the real puzzle, and our goal today, is figuring out how to teach a computer to do the exact same thing.
And if we're going to teach a computer, we have to be super clear. We need to define exactly what we're looking for. So what is a common prefix anyway?
So here's the deal. A prefix is really just a fancy way of saying the starting part of a word. And we're on the hunt for the longest one that's a prefix for all the strings in our list. That's the key part. Not just some of them or most of them, every single one has to have it.
You know, the best way to really wrap your head around something like this is just to look at some examples. So let's do that. We'll use the ones right from the source.
Okay, let's start with our list. We'll go character by character. First up, the very first letter. In flower, we've got an F. In flow, an F. And in flight, another F. Perfect. So far, our common prefix is just F.
All right, let's keep going. What about the second character? We've got an L, and an L. Awesome. So now our shared prefix has grown. It's fla. Okay, but this is where things get interesting. Let's look at the third character. Flower has an O. Flow also has an O. So far, so good. But flight, nope, it has an I. And that's it. Game over. The chain is broken. The second we hit a mismatch, we have to stop. So the longest one they all shared was just fla.
Okay, let's try another one. How about dog, race car, and car? Well, we look at the very first letter and we hit a brick wall immediately. We've got a D, an R, and a C. They're all different. There's absolutely nothing in common right from the get-go.
And this brings up a really important rule. This is straight from the documentation. If there's no common prefix, what do? You return an empty string. It just makes sense, right? No common ground, nothing to return. So, we've got the intuition down. We can see it with our own eyes. But how do we turn that feeling into a step-by-step recipe that a computer can actually follow? Well, let's break down a really simple but super smart strategy.
So the strategy is basically this. First, you pick one word to be your, let's call it the benchmark. It's going to be our guide. Let's just grab the first one, flower. Then you walk through that benchmark word one letter at a time. You take its first letter, F, and you go ask all the other words, hey, is your first letter also F? If everyone says yes, great, you move on to the next letter, L. The very instant one of those words says, nope, my letter's different, the whole thing stops. You're done.
That logic seems pretty solid, right? But nothing beats actually seeing it work. So let's visualize exactly how this algorithm plays out step by step.
Okay, here we go. We grab the first letter from our benchmark, F. We check it against flow and flight. Yep, we've got a match. Green light. Next up, the letter L. Check it against the others. Another match. We're good to go. Okay, now for the third letter, O. We check flow. It has an O. Perfect. We check flight, and whoops, it's an I. Mismatch. Red light. The algorithm just slams on the brakes right there.
And this is the really efficient part. The algorithm doesn't bother checking W or E or R. Why would it? The moment it found that first disagreement, it knew the common prefix couldn't get any longer. So it just stops and returns everything it had built up so far. In this case, flat. So this feels super fast for just 3 words. But if you're thinking like an engineer, the next question is always, how does this scale? How efficient is this really? Especially if our list of words gets huge. Well, in the world of code, we measure this with something called time complexity. And for this method, it's called O of n times m. Now, don't let that alphabet soup scare you. It's actually pretty simple. All it means is that the time it takes to run depends on 2 things. N, which is how many strings are in our list, and m, which is the length of the common prefix. So, worst case, we have to check every character of our prefix against every single string. And think about why this matters. If you're building something like a search bar with autocomplete, it has to be lightning fast. So efficiency isn't just some nerdy detail. It's everything to the user. Okay, so we've talked through the logic, we've seen how it works visually. Now for what's, kind of the most satisfying part, seeing how this clean, simple idea turns into actual code.
And what I think is so cool about this is how cleanly our logic maps to the code. It's almost a one-to-one translation. Picking the benchmark and going through its characters, that's our first loop. Comparing that character against all the other strings, that's the second loop inside it. And stopping and returning what we have so far, that's our return statement right there. It's just a really beautiful direct implementation of the idea we came up with.
So let's do a quick recap of what we just did. We started with a clear problem, we used examples to build up our intuition, then we came up with a solid strategy, we watched that strategy in action, and finally, we saw how that logic translates directly into code. Pretty solid journey.
So we've totally nailed this for up to, say, 200 strings, which is what the source material talks about. But I want to leave you with a final thought. What if it wasn't 200 strings? What if it was 200 million? Would this character-by-character approach still be fast enough? Or would you have to throw it out and come up with a completely different, maybe even crazier strategy? Something to chew on.